Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Helic with Anand Raman, who's going to talk today about electromagnetic crosstalk. So, Anand, what is electromagnetic crosstalk?
Electromagnetic crosstalk is any unintended communication between what's typically called an aggressor and a victim that causes undesired behavior in the victim signal. So the idea is there is some signal that is sharing energy with a victim signal and changing the behavior of that victim signal in a way that you do not want. And the mechanism for that could be through the electric field or the magnetic field, hence the name electromagnetic crosstalk.
This is not a new concept. People have been working in the analog space, have been well aware of this for some time. Why is it becoming a problem that's now spreading into the digital world and the mixed signal world?
Great question. You're right. This is nothing new from a physics perspective or even a concept perspective in IC design. People in the analog RF world have lived and dealt with this for decades. Why it's becoming more interesting now is that traditional digital design that has typically not thought about this problem is running into this problem almost on every single tape out. And why that is happening is because of sort of three related trends. One is the need for more and more speed. The operating frequencies are getting higher and higher. And at these high speeds, the magnetic field is important and relevant and plays a significant role that people have traditionally not thought about. Hand in hand with this increasing speed is the move to lower and advanced nodes and higher and higher integration. These two trends mean that you're forcing in multiple blocks into small areas, exacerbating this problem even more. So these three things together have made this problem more relevant and more important and seen more regularly in what is called traditional digital design.
As we start getting into these advanced designs, one of the problems that we're running into is the power delivery network, which is a pretty noisy network, right? How does that start affecting electromagnetic interference of any sort?
Electromagnetic interference has multiple channels, often all of them operating in concert. The power delivery network is effectively a conductive fabric that's everywhere in the SoC, which means that it could allow energy from any part of the design to effectively couple to any other part of the design, and therefore is an important channel that needs to be modeled properly if you want to eliminate a risk from electromagnetic coupling. Please do understand, however, that that's not the only channel. The substrate can play a role, even free air can play a role. And it's often a combination of all of these that fully represents the problem. So modeling just one of them by themselves is not enough. You need to model the victim and the aggressor in context.
Why don't you draw this out for us?
Sure.
So what are we looking at here?
Here's a schematic high-level representation. Consider a part of a design and let's say two blocks, and we're going to arbitrarily call one of them the aggressor and the other one the victim. The idea here is energy from the aggressor is coupling into the victim and changing the behavior of the victim in an unwanted way. What are the ways in which this energy could couple? First of all, there's the power distribution fabric, or maybe some combination of power distribution and other routing. That's number one. There's just air, free space, dielectric. There's just direct coupling through air from the aggressor to the victim. And three, there's the substrate itself. These two blocks are built on top of a common substrate, and the substrate represents a channel through which energy can couple.
Does it matter what the substrate is? If it's silicon or bulk silicon, or does it matter if it's FDSOI?
Great question. FDSOI, as an example, does provide some insulation for the electric field because there is a layer of insulator between the metallization and the silicon. However, from a magnetic coupling or field perspective, it plays little to no role. So if you look at the holistic concept of electromagnetic coupling, the substrate plays a role for just a part of it. So it is important to know what kind of structure you're modeling, but there is no single bullet remedy that says move to a FDSOI substrate and you solve the problem.
What effect does the package have? Because the package is becoming much more complex as time goes on.
Sure. The package simply represents yet another channel through which you can have electromagnetic coupling. What's happening with advanced nodes and advanced packages is the distance between the metal layers of the package is decreasing. Gone are the days when the package layer was 200 microns away. Now they're 50 to 60 microns away, which is comparable to the distance between the substrate and the top metal layers in the chip. What this means is, apart from the three channels I've drawn on the board, metal layers in the package represents yet another channel through which there can be EM coupling between an aggressor and a victim. So it just makes the problem worse.
So one of the solutions to this has been building extra circuitry margin into a design. You can't necessarily do that anymore at the most advanced nodes. What impact has that had on electromagnetic interference?
Great. So you're right. The most common way that people circumvent the problem is, instead of modeling it accurately, which is complicated and difficult to do, just build a lot of margin into the design itself to try and work around the problem. Let me take a second to explain margin. Margin can come in different forms. One is just spacing or white space. Just keep sensitive things far apart and use empty space, which is expensive and difficult to do at advanced nodes. Or it can be spending a lot of energy to shield the critical routing with metallization all around it. But that translates to requiring more power in the buffers to drive them, more real estate, disrupting the power delivery fabric because you've done some complex shielding structures, or even to add more buffering to drive high-speed signals. All of these actions either require more silicon, more power, or both. That's becoming less and less affordable, and therefore the designers are confronted with the problem of having to model it accurately and get it right because of the economic pressures of requiring lower power and lower real estate.
Why does this have to be done with every new design? I mean, you think that with known good blocks that this should work. What's the problem?
The problem with known good designs is context. So let me illustrate that with a quick sketch. Let's assume you have a really well-characterized VCO block or some block that has either been provided by a third-party IP provider or it's from past designs that have been successfully characterized. And this block is really well understood at its interfaces, really well characterized, successful in silicon. However, the context into which it fits into this particular design and this particular application is going to vary from every other design it's been used in. And as we discussed previously, if you happen to have some sensitive signals here, which we are now going to call the victim, and perhaps this is the aggressor, it could even be the other way around, but let's start with this assumption. There are multiple channels through which the aggressor can couple to the victim. And these channels have now changed. The substrate may be different, the power delivery network and the routing may be different, and the physical distance between the two may be different. And that means that what worked once before may no longer work in this new context, in this new application. So you will need to reanalyze and capture the detailed model to make sure that there is no unwanted interference.
And what's the impact of that? Is it power? Is it performance? Is it just the chip doesn't work? What happens here?
It could be any and all of the above, right? In the worst case, it's a non-functional chip, right? In sort of the most common case is reduced functionality. What that means is the chip doesn't fail outright, but there are certain modes or certain modes of operation that don't work as expected. Now, there's ways around that, which is in software disable those modes of operation, or you could analyze the problem and eliminate it altogether.
And this has shown up in some rather popular products too over the past few years, right? Where people are developing these advanced systems and something doesn't work because of electromagnetic interference, and as a result of that, they have to do a software workaround.
Absolutely. So common examples could be extremely high-speed channels that are supposed to work completely independent of each other. However, in silicon, you find that there is some sort of dependency based on proximity. And so you use software to disable certain modes of operation that force nearby channels operating at the same frequency. That's just one of several examples. Now, this leaves behind functionality on the table, which translates to real dollars.
There are some unusual effects here as well that most people working in the digital space don't understand. Things like snapping to the same frequency, right? What is that?
That's a concept called Vco Pulling. So for example, if there are two VCOs that are somehow coupled through any of those 3 or 4 mechanisms we talked about before, if the coupling is strong enough, when the VCOs get within a certain percentage of the operating frequency of each other, one of them will snap to or get pulled to the oscillation frequency of the other. Even though in theory they're supposed to be able to operate completely independently, in practice, because of if there are coupling mechanisms, one will pull the other VCO, one VCO will pull the other VCO to its frequency of operation. This is an undesired behavior, as you can imagine, especially if these two VCOs were supposed to be completely independently programmed to operate at different frequencies.
So as we get into very complex designs, it becomes harder to nail down how a system is going to behave. You have not only complex circuitry, you also have complex use cases. So one person's use case may be different than somebody else's. How do you deal with that, and what impact can that have on electromagnetic interference?
Good question. The problem is that there is not going to be a bounded set or bounded combination of aggressors and victims that you're going to be able to analyze and sign off. As we talked about before, the coupling mechanism between potential aggressors and victims is numerous. I mean, yes, we generalize the power delivery network as one thing, but trying to capture all possible channels between a pair of signals is, first of all, hard. And even identifying what's a potential aggressor and what's a potential victim can be challenging. So this is where there needs to be a sort of a combined approach. There are going to be some obvious pairs of things to look at. Extremely high-speed signals are classic aggressors or victims. There are certain physical structures that should be looked at. Scribe lines and signal rings as an example. The first package layer is another example. However, beyond that checklist, there is a strong need for the designer to use their design knowledge and based on the particular application and functional modes, identify potential pairs of aggressors and victims and model those and sign off on them.
This is more probabilistic than it is finite, right? There's no specific number. It's more, this is where it's likely to cause a problem.
That is correct. Any automation or assistance that points the designer into areas that they may not have thought of is going to be of great help. There is also the general idea being you reduce the risk to a acceptable amount rather than completely eliminate 100% of the risk. The goal is to get the top X% of the worst case offenders out and then hope that design margin captures the rest.
Where does this fit into the traditional flow?
So where this fits into the flow is the earlier in the flow you can start accounting for these types of effects, the lower the load is at the end of the flow. So the answer is actually everywhere. So beginning right at the stage of floor planning, when you are laying out the top level blocks in the design, the critical nets, the power and ground routing, the seal rings, it is a really good idea to have a good sense for the level of isolation between potential victims and aggressors. And as the design evolves, it makes sense to have checkpoints. And part of this checkpoint process is identifying potential victim and aggressor pairs. And part of that, a subset of that, is designing test benches that test for whether, if there is coupling between what you suspect as aggressor and victim pairs, that it is indeed affecting the performance of the design. And in the end of the design, at the end of the design cycle, when you do physical verification sign-off, we believe it's extremely critical for the designer to be able to sign off electromagnetic coupling as part of the physical verification sign-off flow.
Anand Raman, thanks for a great explanation of a very complex subject.
Thank you. My pleasure.